This lecture is on biogeochemical cycles. It's a lecture from chapter 3. There are many important cycles in the environment. Of particular importance in environmental science are the biogeochemical cycles, which trace the movement of chemicals that are essential to life. In this lecture, I will introduce the carbon, phosphorus, nitrogen, and hydrologic cycles. If you think about the term biogeochemical, it's a compound word. These cycles involve biological, geological, and chemical interactions. So nutrients circulate through ecosystems, and they move continuously, right, through biogeochemical cycles. When I say move continuously or circulate, they move through the air, water, soil, rock, and living organisms. When we're looking at the biogeochemical cycles, we can talk about pools and fluxes. A pool is a reservoir, okay? It's a temporary storage area for the nutrient. So it's a place where the nutrients remain for a certain amount of time. And that varying amount of time is called the residence time of the nutrient. Flux is the movement of the nutrients between or among pools. We can think about the rate of flux and the amount that's being moved between the pools, and when we're looking at changes over time in these cycles. Let's start with the carbon cycle and talk about some of the main parts of the cycle. Let's start with a little bit of a discussion of the pools. The main pools of the carbon cycle are sedimentary rock, which is the largest pool of the cycle, oceans, which is the second largest pool, right, or reservoir, the atmosphere, and land plants and consumers. Okay, these are some important pools or reservoirs for the carbon cycle, I guess, including soil and soil biota. Biota meaning living things, the things that live in the soil. Some important processes that we'll look at in the carbon cycle are photosynthesis, right, which is shown here, GPP, gross primary productivity, right? This is the intake of carbon, right? If you look back at your photosynthesis equation, from the atmosphere into plants, okay, whether they're algae in the ocean, right, or land plants. The return of carbon from living things back to the atmosphere is via respiration, okay? So here's respiration from consumers, here's respiration from land plants. Remember, respiration is the taking of the glucose and breaking it down to get that potential energy between the bonds. You can see up in the upper corner here, there is a special kind of a breakout for the oceans. Many of the same processes that are occurring on land are occurring in the oceans, and there is an exchange between the atmosphere and the oceans. So gross primary production, right, the plankton in the ocean, the organisms, the producers, bring in the carbon dioxide from the atmosphere, and their respiration, as well as the respiration of consumers, right, brings carbon dioxide, or releases carbon dioxide back into the atmosphere. Some of the carbon is decomposed, okay? So when land plants or consumers die, some of that carbon gets taken in by the soil and the soil biota and is broken down and stored in the soil, and eventually may become part of sedimentary rocks or fossil fuels. Another important idea here is that you have in the sedimentary rock, you have fossil fuels, the remains of organisms that have been compressed and changed into coal, oil, or natural gas. So these really are fossils of organisms. There's a very long residence time down here. This pool or reservoir is one that is very much disconnected from the terrestrial and atmosphere. However, one of the important ideas here is fossil fuel extraction, right, and then combustion, right, of fossil fuels leads to the carbon dioxide that was once locked up here getting into the atmosphere. Another key important point here is net deforestation. As we deforest the planet, there is a reduced uptake by plants, right? And if they don't uptake the carbon dioxide through gross primary productivity, right, it stays in the atmosphere. So that's a quick look at the carbon cycle. And I should point out that the numbers, right, in the reservoirs shows how much is there. So that's how I can tell that the sedimentary rock is the largest pool, and that the oceans, right, is the second largest pool. There are a number of impacts of humans on the carbon cycle, and some of them we've talked about. First one is the burning of fossil fuels. So taking those fossil fuels from deep in the earth, harvesting them, and then combusting them releases carbon dioxide. Second one, cutting of forests and burning of fields moves carbon from organisms, right, the living plants, to the air. So that's that deforestation. We've been measuring carbon dioxide for some time, and we'll talk more about the details of how much carbon dioxide is in the atmosphere in a later chapter. But today's atmospheric carbon dioxide reservoir is the largest in the past 800,000 years. And this is the driving force behind climate change, increasing carbon dioxide. Okay, this is the phosphorus cycle. Okay, the phosphorus cycle, like the carbon cycle, is going to describe the routes that phosphorus atoms take through the atmosphere. I'm not going to spend as much time on this one. I want to note a couple things though. First of all, there's no significant atmospheric component. Okay, so there is a small amount of transport of phosphorus in the atmosphere, but it's a very, very small part. And so for the most part, phosphorus is within the rocks, and it's released by weathering or breaking down of those rocks. Phosphorus has low environmental concentration, so it's not widely available, and so phosphorus is needed for plants to grow. Okay, so plants need phosphorus as a nutrient, and so phosphorus is a limiting factor for plant growth. There's not enough of it for many plants. Not all plants, right? Not all soil types, but one of the important places where we see phosphorus limitation is in Minnesota lakes. So most lakes in Minnesota are limited by how much phosphorus there is available for the algae or phytoplankton. We've had some impacts on the phosphorus cycle. Here's a few ideas. The mining of rocks for fertilizer moves phosphorus from the soil to water systems. Like I talked about, this can cause too much growth of plant life in lakes and streams. Wastewater discharge also releases phosphorus, which boosts algal growth, right? The producers in lakes and streams, and causes eutrophication, meaning too much algal growth. Phosphorus also is present in some detergents, and we all should be cognizant of whether or not we're buying phosphate-free detergents and the impacts of our not buying phosphate-free detergent if we aren't. Also, there's been a lot of attention to not using phosphorus in fertilizers if the soil isn't phosphorus limited. Okay? This is the nitrogen cycle, also a very important and complex cycle, and I want to just talk about a couple things in the nitrogen cycle. Okay? Now, for the nitrogen cycle, the major reservoir is the atmosphere. Look at this. This is where most of the nitrogen is. It's in the form of this molecule, N2, so two nitrogen atoms connected together. This is a triple bond. It's a very, very strong bond, okay? And the nitrogen that is in the atmosphere, right, which is about 78% of the atmosphere, is what we call inert, right? It's very stable, and it cannot be used by living organisms to meet their nitrogen needs. For it to be available, it needs to be fixed, okay? It can be fixed by lightning, it can be fixed by living organisms, and it can be fixed by our processes where we make nitrogen in factories, okay? This fixation process is called nitrogen fixation, okay? It's when you take nitrogen, that N2 form, right, and you make it into a form that is available to organisms, this ammonium form, okay? This form is an available source that can be taken in by plants, okay? Animals obtain nitrogen by getting it from eating plants or other animals. So animals don't get nitrogen directly from the environment in that form of ammonia. They have to get it from other organisms. The last important thing I want to talk about in the nitrogen cycle, and there's a lot of details we're skipping over here, is the process of denitrification, which takes the biologically available form and brings it back to nitrogen gas, or N2, which is in the atmosphere. And this is done by bacteria. We call them denitrifying bacteria. So denitrifying bacteria do the process of denitrification. Humans have had a pretty broad impact on the nitrogen cycle. So here are a few of the important ideas that I want you to think about here. As you can tell from reading the central case in this chapter, excess nitrogen leads to hypoxia in coastal areas. Hypoxia is the problem where there's not enough oxygen. It creates these dead zones where organisms can't live. Secondly, synthetic fertilizers doubled the rate of Earth's nitrogen fixation, okay? So in the past, right, we were not able to fix nitrogen in factories. We now figured that process out. It's been great as far as our ability to grow more food, right? But it's had some consequences in that there's a lot more nitrogen out there and some negative impacts. The burning of forests, so deforestation and the use of fossil fuels, which give off nitrogen, lead to acid precipitation. Okay, we'll talk about this later on, but you've probably heard of acid rain. This is when rain falls through the atmosphere, it picks up some of these nitrogen compounds, and you get what's called nitric acid built, and can be pretty bad, especially in some areas where there's not a lot of buffering capacity. We've seen an increased emissions of nitrogen-containing greenhouse gases. Okay, so it's not just carbon dioxide that's a greenhouse gas that's involved in climate change. There are also other ones that we'll talk about later again, and these are nitrogen-containing. Other nutrients like calcium and potassium in the soil can be washed out by nitrogen fertilizers, okay, so that they're not available, and the soils can become have a dramatic decrease in those minerals. Last on this list, we're seeing a reduced biodiversity of plants adapted to low nitrogen soils. Okay, so the organisms that once were able to live in places, right, where nitrogen was naturally low are being displaced by plants now where we see more nitrogen available. Those plants are being displaced because they can't compete anymore for that area. Here's a graph showing nitrogen right here in millions of metric tons on the y-axis from 0 to 8, and over, down to the bottom it's year. And we've got some different sources of nitrogen here, and we can see that nitrogen from animal manure has stayed pretty stable. We've seen an increase in nitrogen fixation from legumes. Legumes are plants like beans and peas and soybeans that have the ability to fix nitrogen, do that biological fixation. Actually, it's the bacteria that live in their roots that do it. So we've seen an increase of planting of these legumes and causing more available nitrogen, and we've seen a dramatic increase in fertilizer as we have learned, right, how to fix nitrogen in factories and make it available for agriculture mainly. I want you to be aware as you're reading through the central case on hypoxia that there has been a law that addresses hypoxia in the Gulf. It's called the Harmful Algal Bloom and Hypoxia Research and Control Act of 1998, and it called for an assessment of hypoxia in the Gulf and for the following other conditions: to reduce nitrogen fertilizer used in Midwestern farms. Remember, those are the places where much of the nitrogen is coming from. We need to change the timing of fertilizer applications to minimize runoff. So looking at precipitation and other factors and try to keep that nitrogen in place rather than running off and eroding into the Mississippi River. Investigate the use of alternative crops that don't need as much nitrogen. Manage the livestock manure. Remember, manure is going to be a source of nitrogen, and again, that's going to get in the river. We really need to work on restoring wetlands and creating artificial wetlands, especially in the Gulf of Mexico, but everywhere. Right, wetlands have been taken out in many places around the globe, and they have a lot of important functions in keeping things working properly. The law also calls for, or the act also calls for, improved sewage treatment technologies and an evaluation of these approaches. It looks like the act has worked out, and it was reauthorized in 2003. The last cycle here I want to talk about is the hydrologic cycle, or the water cycle. And I want to peek at a few important parts of the cycle. Now, water is essential for biochemical reactions, right, and is involved in nearly every environmental system. And the hydrologic cycle summarizes how liquid, gaseous, and solid water flows through the environment. The oceans are the main reservoir for water, and less than 1% of water is fresh water, okay, available as fresh water. So there are other, so 97.5%, something like that, of the world's water is in the oceans. Some important ideas here, of course: precipitation from the atmosphere, evaporation, as water is evaporated and brought into the atmosphere, forms clouds and precipitation occurs. You've got runoff that we've talked about from rivers and streams. We've got extraction for human use, right, either from the ground or from surface water. And we've got transpiration, which is one you may not have heard of before, which is the essentially water loss from plants. So we sometimes call that evapotranspiration. And then you have the process of infiltration, right, which is the water that soaks into the earth, becomes soil water, or maybe groundwater. And when we talk about groundwater, we talk about the terms aquifer and water table. An aquifer is an underground reservoir of sponge-like regions of rock and soil that hold the groundwater. The water table is the upper limit of groundwater held in an aquifer. This groundwater, right, can be very old, so there can be a very long residence time of groundwater, and that can be an issue if we're extracting it too fast. It won't be replenished, it's not renewable. Here's some human impacts on the hydrologic cycle that we'll be discussing some of those as we go on in class. First of all, damming of rivers increases evaporation and infiltration into aquifers. Altering the surface and vegetation increases runoff and erosion. Spreading water on agricultural fields depletes rivers, lakes, and streams and increases evaporation. Overdrying of groundwater for drinking, irrigation, and industrial uses depletes groundwater resources. Removing forests and vegetation reduces transpiration and lowers water tables, and emitting pollutants changes the nature of precipitation. In conclusion, understanding of biogeochemical cycles is crucial, and humans are causing significant changes in the way these cycles function.